name is Ford Oster, and this is a proof of existence and uniqueness of the remainder and quotient according to the remainder theorem. This proof was worked on in conjunction with Nicole Campagna and Sam Gassman. And the uniqueness of the remainder quotient PDF was used, as well as the YouTube video division algorithm proof by Math Matters as resources. Alright, so first we're going to prove the existence, and to do this we're going to use the equation n equals qm plus r, and the set is defined as n minus xm, and this set is the set of all integers of the form n minus xm. And we'll use it as the smallest integer is going to be used to represent the remainder that satisfies the remainder theorem. And to do this, we're going to first find cases that satisfy n minus xm is greater than or equal to 0. And to do this, we're going to split this up into two cases. These two cases are n is greater than or equal to 0, and n is less than 0. Alright, and so first we're going to work with the first case. And to do this, we're going to let x equal 0. And by this case, you can see that when x is 0, it causes this statement xm to become 0. And so then the statement is just n is greater than or equal to 0. And that is given by this case. And so this implies that n is an element of the set S. And now for case 2, we're going to let x equal n, and then doing the same thing we did for case 1 by plugging in the new x, we're going to do the same thing here, where we get n minus nm, and then this can be simplified to n times 1 minus m. And by doing this, we can see that when m is 1, it causes this part of the equation to go to 0, which is what we want to hold the equation true. And then when m is greater than 1, we get a negative number, and that's fine because in this case n is given as a negative number, and a negative number times a negative number is a positive, which is what we want to hold true. And so this implies that n minus nm is an element of S. And so this, having these two cases hold true shows that there is at least a element in the set S, which then holds true by the well-ordering principle. And so now we want to find or show that the lowest least element in the set, which we're going to call R, is less than m. And to do this, we're going to prove by contradiction. So we're going to assume that R is greater than or equal to m, and this implies that n minus qm is greater than or equal to m. And now using some basic algebra, we're going to get n minus qm minus m is greater than or equal to 0. And then we're going to simplify that a little further and get n minus m times q plus 1 is greater than or equal to 0. And then we can see that this is a false statement because n minus m times q plus 1 is less than n minus mq, which is equal to r. And therefore, by contradiction, we can see that 0 is less than or equal to r, which is less than m, therefore proving the existence. Alright, so next we're going to prove the uniqueness. And to do this, we're going to use the equations n equals q1m plus r1 and n equals q2m plus r2. And the idea of this proof is to show that q1 equals q2 and r1 equals r2. And so first we're going to set the two equations equal to each other by substitution, since both the equations given are equal to n. And now we're going to use some basic algebra to manipulate these equations so we can get q1m minus q2m equals r2 minus r1. And then we're going to simplify a little bit and get m times q1 minus q2 equals r2 minus r1. And now we're going to create a new variable and let q prime equal q1 minus q2. And then we can see that q prime times m equals r2 minus r1. And so now we're going to just pause here for a moment and come over to here where we have 0 is less than or equal to r1, r2, which is less than m. And then we're going to multiply the r1 version of this by -1, which gets us negative m is less than negative r1, which is less than or equal to 0. And then we want to combine the now edited version of the r1 inequality with the untampered r2 inequality. And that gets us negative m is less than r2 minus r1, which is less than m. And from the previous equation that we have manipulated, we have that q prime m equals r2 minus r1, and here we have r2 minus r1, so we can substitute in for that q prime m, which is less than m. And so now we're going to let q prime equal to 0, which allows this equation to continue to be held true. And so now we can see that that all goes to 0, and so we have 0 equals q1 minus q2. And now after moving around the variables, we can get q1 equals q2, showing that this part of the proof is true. And then using the same idea of plugging in the 0 into the equation we have 0m equals r2 minus r1 from this equation. And we can get that 0 equals r2 minus r1. And then doing the same thing we had here by moving the variable over, we can see that r1 equals r2, which then shows the uniqueness of r as well.